this question. There was nothing, there was no pressures. You had to calculate. Like in test, some of you went and, like I never asked you for that graph. Some of you went and did all the direction and created the graph. So read and understand the question. So I'll go one by one. I'll go now to the model answer. I hope I don't open the 2019.
2019, we take pictures.
It's recording.
Okay, so when you do this, see, all I did, all my data, I put it there, simple, you get 2 marks. That's what the number pattern or the numbering schedule is exactly almost the same, 95% is the same, slightly here and there, but I mean, don't need to worry about the close. That's only for my own, like because I'm a lecturer, so it's different in my case. So I have to, it has to go through a review process and everything, and then it has to go to the archive box. That how, what is I'm marking the student against. So I have to submit a copy to the department. So all I need to know, okay, that's important to me, that's important to me, that's important to me, and then this one. Terrain category, of course, you will go down and do it. So if you have done that, you get the 2 marks and the building dimensions. Then the next is the formula. If you write, the regional wind speed, if you do this, it's another mark. And in this case, we got 45 because it's Christchurch, and Christchurch is A7, I think. A7 or A6, one of the region, but yeah, it's A7. Then the terrain height multiplier, again it's easier, the height is given, the terrain category is given, it's TC2. All you have to go to the table and calculate MZK. In this case it's 0.964. And then for the other direction, because the directions are given, it's terrain category, sorry, it should be the other way around. 2 and 1, that should be around, other way around. So, but the numbers are right, it's based on the, no, it should be okay. Yeah, 2 and 1, it's okay. So, then coming down, the shielding multiplier. So, the shielding parameters be given. That's how we calculate again the shielding multipliers. And then topographic multiplier. That's because we are 650 above the thing. So, whatever E is there is the formula, so it comes up from above. Then direction multiplier. So we have, because we have to create a design wind speed, so that's all the 8 directions. Sorry, we need 6 direction only, because for the portal frame, if we have, let's say there's the portal frame, let's say there's north and south, so I need those 2. That's the 6 direction that I need, right? That's it, and then that's why I put those 6 directions there. And then I create, this is all my side wind speed that I created and the data above that I have done. Once that's done, see each. So if you have done this direction multiplier, because you need them, they have 2 marks. And then putting them into this table to find out the side wind speed for all 6 directions, that's it, that's an additional 4 marks and a total of 15. Now it comes to the design wind speed. So the design wind speed, see, for the north, it's 44. It's the mix of those 2, the direction, and then 45 degree each direction. Similarly for the south, 45 degree each direction. And these are the 2 design wind speed. That's 2 marks, that's 17 marks, and it's done. Okay, now let's go to question 2 now. So question 2, a steel beam, I think, was the test similar? Test was similar. Yeah, similar but different numbers, right? So you got a simply supported beam there. You are given the UDLs, G and Q. The UDLs are given, and then what do you have to do? All you have to do, okay, the first is calculate design actions. So design action means bending moment, shear force, that's all. And that has 4 marks, easy marks. That's why you score more in I think in the test. So Then part B, check the nominal member capacity of the specified member and the adequacy of the above section. So then you have to go and find out the moment and shear capacity for that. Knowing that UB section is a stocky width, check the shear capacity of the selected beam at A. So then you shear capacity, and then the last, deflection. So for the deflection, you are given the load case, you are given the moment formula, you are given the deflection formula. Then let's go into the so the first G, Q, I write down all the loads, and that's 2A, so W is equal to 13.8, 1.2 G plus 1.5 Q. M design is equal to that, V design is that, that's 4 marks. That's what you did in the test, most of you. Some of you got it wrong, but most of you got it right. Then the next part would be, I would have done this after. I should have done the section capacity first, but doesn't matter. So the first thing is, let's go to that. First, this should be coming first because we should start here. We should find out the section capacity because we can't move further till we know the section capacity. So section capacity 222 and design is 99 and it's okay, 2 marks. Then we go and trying to find out the member capacity. Now the member capacity is equal to alpha M, alpha S and MSX. Now we don't know alpha M and alpha S, therefore we go back. So to find out alpha S, we need to find out effective length. L is 7.2 meter, KT1, KL1, KR1, effective length is equal to 7.2, and then from the table, FL is equal to 7 meter, alpha S is equal to 0.29, FL is equal to 2, alpha S is equal to 0.24. And then interpolation. So that's for the effective length, calculating that, you got 3, and then for calculating alpha S, you got 2.5. Then the next is the moment modification factor. We got this formula here because it's a simply supported. You can, when it's, even in the assignments, you consider segments, right? And your moment diagram never fit that because you just taking, for simply supported beams and things like that, you can assume that fix in one span, but when you trying to find out, split the beam into segments, then it's really hard to justify those cases. So the easy way is just go and use the formula, right? But in the exam, it will be, if it's even if it's the formula one, it will be quite simple. So not going to be the hard, the curve. It won't be the curve one, right? So because the curve one is quite hard to find out the moment at those different locations. While in the assignment, you had the tools, you had the multi-frame to find out exactly where to. If you couldn't do, just split the beam into 4 segments. Like that you can in multi-frame. That you can divide, right? Okay, your segment is at 1/4. You divide it there, and then that segment there, divide that to 4 again. So then it will give you the numbers at those 4 points. You know what I mean? So let's say you got a column, a beam, right? So the first quarter point is here. So I split the beam there. Put a joint there. There is a node now. So this is a separate member. This is a separate member. In terms of just giving me values. Then this member I'll further divide to 4. So then the moment diagram, when it's, let's say it looks like this, it will give you a value here, value here, value here, value here. And you just pick it from there. Easy as. Right? You can do that in multi-frame. So, but in this case, it's a simply supported beam. That's the case 5 or 7. I can't remember. But one of those cases, all I have done rearrange formula. Most of you got it right. And the assignment, and we get around 1.13. When it's simply supported beam, straight away, it's 1.13. When it's simply supported beam with a point load and a triangular moment, straight away it's 1.36. It's that simple, But in any exam, you have to use the proper way. Because otherwise, you're not going to be given marks if you don't put the formula there and just put the number. Because I don't know where you might have just be looking at the shoulder of your mate, copy from there, write it down, So that's not, don't expect that. Then once I found out, then the most important is make sure that alpha S and alpha M is less than or equal to 1. In the assignment there was quite a few who didn't do this, and your member capacity was greater than section capacity, which is not the case, right? So in this case, my member capacity is down here, it's not good, so then I went, increase the section, repeat the same process again. You don't need to do you just need to calculate the alpha S only, that's it. Your alpha M remains the same, effective length remains the same, no changes. It's just the alpha S, recalculating is just the alpha S, that's all. So that is, then we go to question, the next part, the shear capacity. As long as your moment capacity is less than 75%, the shear capacity is equal to VV, is equal to VVM, right? Otherwise you have to do the ratio, that proportion method, and they use the formula to find out. In this case, because it's less than 75% of the section capacity, so that's okay. You can just stop there, don't need to go and do all that additional formula. A simple check, is your moment 75%, more than 75? Yes, okay, do that check. If not, you just stop there, that's simple. Then the next was, the last part was deflection. So G, Q, short term is given, length is given, you find out this is load, and the I, because the table was given to you, so you have to go and pick up what is the Ix for that, and find out the deflection. And that was easy 4 marks in 2017 exam. Now let's move on to question 3, which is the right, the hard part. The thing is, most of you got the connection. Like it was so simple. I did the entire flange. There was, for you. Sorry, the splice connection. There is 2 parts to the splice: a whip splice and a flange splice. Flange splice is the simplest one, right? It's straightforward. So all you have tension force there, which comes from the moment, and the flanges, top and bottom flange. So you have flanges. There's the beam. So there is moment, for example, that create tension and compression. And that tension there, so we start, and the bolts is equal to that tension. That's it. Right? You don't need to go and do all the, like some of you went and do that, okay, eccentric moment, where it's come from, all the X and Y and Z, and that, but there was not the answer I was looking for. Right? It's simple, that the flange splice is the simplest one. So you find out that tension. Can your plate follow the load path? From the flange, it goes to either to the weld. You either start from the weld or either you start from the bolt. So whatever is above is exactly the same thing below. So you start with, let's say we're doing the flange splice first. Where does the load go from the flange? It goes to the bolt. What type of force it is? Shear failure. What type of failure? If I'm trying to load that bolt, it's shear. So how many bolts do you have? 4, 6, 8, 10, 12. That tension that you have in here, tension compression, is equal to M divided by D, and D is equal to D1, which is center to center of the flange. That's it. Then after that, from the bolt, where does the force go? To the plate. Right? In the plate, what type of failure mechanism it is? 2 types. No shear. Tear out, which is the tensile capacity of the net cross-sectional area, and bearing. Those are the two. Then from the plate, where does the load go? Back to the connection on the other side, whether it's bolt or weld or, and then back to the flange. So in our case, it's the weld. What is the weld length available all around? Let's say 200 millimeter. What is this tension? So T divided by L weld, that gives you, let's say, X kilonewton per millimeter. Go and check in the table, easy. You know, check in the table what weld size has this capacity and pick that weld, that's it, simple. That is all about the flange. Now coming to the whip. Some of you use the moment in the beam, which is not the case. Some of you use axial load, you know, there was lots of things. Simple is, let's say one side is weld or both sides is weld, right? There is a shear force in that beam, in that whip. That shear force has to go to the bolts and to the whip splice plate, right? And again back to the weld and to the whip on the other side. Now, there is a centroid of the weld group and the bolt group, and the distance between the two is the eccentricity. Now that eccentricity creates a moment, ME, or eccentric moment, and that's equal to V star, which is the design shear force at that point in the beam, time E. That's it. So now you got the normal shear, which is V star, how many bolts you have, divided by 2, that's your vertical component. Then you have right? Then you have the force, the shear force from the moment. So then it has two components, let's say horizontal and vertical. You go and do your judgment, which is the worst case, and just add to this. And you will find the resultant. That's it, that's your design action, that's your shear force, go and check the bolt. There's nothing hard in it. And then on the other side you got the welds, do exactly the same for the weld. There was the whip splice, and there was a mess, right? So that's all you have to do, it's simple as that. And I did two of them. So we got a column, and then we have a plate attached to it. This plate could be a cobble or whatever, and the load applied there. Right? We did this example in the class. This was another kind of the web example. So now, how do we deal with it? So it's an eccentric load. So to transfer this load to the centroid here, that is the centroid of the bolt group, to apply here. So I have to replace that F with the F here and a moment, which is equal to time E, which is E is this distance here. From here, it's simple. The normal shear is simply F divided by 4, and it's downward. And then you have the moment force, which will have, let's say it's clockwise. And by inspection, that bolt and this bolt, these two are the worst case. Right? Just left to right, right to left, the horizontal component. So this has a horizontal component vertical, and right, so you just add, and that's the resultant. That's it. And then go and check the capacity. Choose the bolt from the table. What's hard in these things? You have to make it simple. You have to understand how the load flow. Remember, follow the load path. If we are getting out of here, trying to get to that car park, how would we go? Should I jump through here? Huh? No. I should go through that door first, next door to the right, staircase to the bottom, door to the right, and straight up those stairs. Exactly the same here. Follow the load path. Everything has a path to go through. Like electricity, it has the